Welcome to Math 31. This is the second part of the Related Rates 2 video. Going to just look at two applications, one travel question, such as we were doing before, and then a pulley question, which is a slight variation on triangle problems that we've seen. So to start, we take a look. Two cars are traveling eastward on parallel roads. So this application's a little bit different than the ones we saw before, where we're talking about cars approaching intersections or leaving intersections. Because here they're both traveling eastward on parallel roads and they are 100 kilometers apart, but they're moving at different speeds. And what we want to figure out is how fast is the distance between them changing at a specific time. Now I'm going to make a quick change here too. I'm calling this 1:30, but this actually should be 1 p.m. Then we'll get something looking like this. So it starts off, we've got the taxi above the other car. Now the way I've got this one drawn, the taxi will be the slower vehicle, and then the other car is the faster vehicle. Wouldn't make any difference if you reversed it. But we do begin with the first car, the one car, totally above the other one. And it will be 100 kilometers apart. So this distance is not going to change. 100 kilometers all the way through. So they'll remain 100 kilometers at 1 p.m. Now, the diagram isn't perfect. It can't be really, given the sort of the nature of this. But what we are trying to figure out is how far at 1 o'clock are these two vehicles going to be from each other. And the second vehicle, the bottom vehicle, is going to be at this point at 1 o'clock when the first vehicle, the taxi, is there. So we would expect the faster vehicle to be further ahead at that point. And I'm going to stick with the regular sort of notation, is that I'm going to call this horizontal distance x, and then the distance between the two vehicles to be z. So we have another right triangle, which allows us to solve this by x squared plus y squared is equal to z squared, Pythagorean theorem. Moreover, because this y value, what I usually call the y value, the vertical distance 100, is going to be the same, always a constant, that goes right into the equation. So we get x squared plus 100 squared is equal to z squared. And we want dz dt, specifically at t is equal to 1 hour. T is not in the equation, although we are differentiating with respect to t. We've got an x, we've got a z, and we'll soon have dx and dz, but we do not have a t. So we're going to have to make the adjustment, which shouldn't be a huge problem. I'm going to differentiate the equation, so that'll give me 2x dx dt plus 0 is equal to 2z dz dt. So same method as always, we differentiate implicitly. I'm going to divide the 2's out so I get a nice easy equation to deal with, and I'll get x dx dt is equal to z dz dt. We do want dz dt. I'm going to take stock of what we have, however. And this is going to require a little bit of play, because the x, the dx dt, and even the z currently are unknown. So we're going to have to do a little bit of work on this one. Now, the x represents the distance of this side. and it's going to be based on the distance, the difference in the two distances. So delta x would be equal to the distance that the red car has gone minus the distance that the other one has gone. So I'm going to write that as in this form, delta, and keeping in mind that the distance of the speedier car, 125 kilometers an hour, if we multiply that by time is equal to 1 hour, which is how much time has elapsed, so t equal 1 hour, that's how far the red car has gone, minus the distance that the taxi's gone, which is 50 kilometers an hour multiplied by 1 hour. So delta x is equal to 125 minus 50 is 125 kilometers. So that's going to be the measure of this side. That's good. That takes care of our x. Then, if we want to get z, we note that x squared plus 100 squared is equal to z squared. And now that we know that x is 75, we can plug it right in. 75 squared plus 100 squared is equal to z squared. So do the math on that, square them, and then take the square root. We should get a clean number. No decimals with this one. So 75 squared plus 100 squared. Take the square root, and you'll get 125. So z is equal to 125. So now that we have that, all that remains is dx dt, and that shouldn't be a huge problem either, because dx dt is the difference in speed. So delta dx dt would be the speed of the fast car, 125, minus the speed of the slow car, which is 50. So that's equal to 75 kilometers per hour. And all we've got to do now is replace everything into this equation and then solve for dz dt. So x is equal to 75. Dx dt is equal to 75. And this is equal to z, which is 125, multiplied by dz dt. So we work this out, 75 times 75, divide by your 125, and you'll get 45 is equal to dz dt. So the distance is changing at 45 kilometers per hour at 1 p.m. So a little bit different, but not a whole lot different. Just differentiate and then look to see what those variables are. There should always be enough information. Now the next and the last question that I'm going to look at is a pulley question. And these ones are pretty common applications, maybe not in real life, but in a course like this. We've got the end of a rope is tied to a box. Now, I'll give the diagram right away so that we can make some sense of this. The other end of the rope is passed over a pulley 5 meters above the ground and is tied to the back of a truck 1 meter above the ground. So the guy in the truck is trying to lift the box or whatever weight that he's got above the pulley. Now the rope is tight in all spots, so there's no slack, and the truck is moving at a specific speed. We want to find out how fast the box is rising when the truck is 3 meters from the vertical line through the pulley. And we'll take our answer to the nearest tenth. The problem with this question tends to be drawing the triangle. Most people get a pretty clear idea that they're looking for or they're looking at a right triangle. But if you take a look at the dimensions that are provided, difficult to know how big the triangle is. And a common mistake is to make the vertical side equal to 5 meters, because that's the height of the pulley is above the ground. In fact, you're better off taking a look at this triangle, because this actually does produce a right triangle. The only difference is that it's going to be 4 meters because we're 1 meter above the ground. And you'll see that that actually does refer to the triangle itself. You're not able to really extend the triangle to the ground. So we work with what we have. And this means that this distance is going to be equal to 4, which I would typically refer to as being y. So that's the first issue. And then, as before, we call this z, and we call this x. I'll put the y there, even though it's equal to 4, because it will become an issue at some point. So there's our triangle. The x is the distance that the truck is from the pulley, the vertical line directly below the pulley. And the 4 should always be the same. So because it's a constant value, it won't change. Then when we read on, we see that we're looking for how fast is the box rising when the truck is a specific distance. So what we note is that we want dy dt. So that's the rate that is changing. Now we would actually expect dy dt to be negative because the distance should be decreasing from the pulley to that where the box is located. Now this is looking a little strange perhaps, because the thing of it is, you're thinking, well, wait a sec, y is equal to 4. It's constant. So how can dy dt be changing when we have that fixed y value? So hold that thought for a second, because it is a problem. Because normally we would expect, if we're having a dy dt, we would expect the y value not to be constant. How could it be constant if we're referring to its change? But hang on just a sec and you'll see where this one is going. Because the equation we will get is x squared plus 4 squared, or 16, is equal to z squared. And then when we differentiate that with respect to time, we'll get 2x dx dt plus 0 is equal to 2z dz dt. And we can then divide out the 2, and we get x dx dt is equal to z dz dt. And now we run into this other issue. So we can only dodge it for so long. We want dy dt. There is no dy dt in the equation. And that explains the confusion that we had earlier with that constant y value. Of course we don't get a dy dt. So we have to look a little bit deeper with this one. Dx dt we can certainly get. Same thing with x equal 3. We'll be able to get the z fairly quickly. Let's do it right now. Because if x is equal to 3, we would get 3 squared plus 4 squared is equal to z squared. So when you work out that triangle, that's just a 3, 4, 5 triangle, we'll get z is equal to 5. So we're set up, except we can only get dz dt, not dy dt. And here we make an important connection. Because the rope is just one rope, the speed that y is going to be decreasing is exactly equal to the speed that z is moving. It has to, because it's the same rope being pulled. So, important note, dz dt is equal to negative dy dt. The only thing that's different is the z value is going to be increasing, the length, where the y one is decreasing. So that's why the sign would be changed like that. So you can do this a number of ways. What I'm going to do is replace the dz dt with negative dy dt. You could also solve for dz dt and then just change the sign. That would be no problem. So I'm going to get 5 times negative dy dt is equal to x, which is 3, times dx dt, which it's supposed to be 0.5. So we multiply all this one out and divide by 5, or negative 5. So 3 times 0.5 divided by negative 5, and it works out to be a clean number. dy dt is equal to negative 0.3. So therefore, the box is rising at 0.3 meters per second. So that will take care of the last related rate problem application that we're going to look at. There's many, many more. With what you have now, most of it's transferable, so you can handle a lot of variety. But it's usually things like this that we just saw that make the difference. Just a little trick or adjustment that you have to make. So thank you for your time.